Good evening, Peter. I hope you're well this evening. Pleased to see you.
Hello. Hiya.
That was a high-pitched voice for Peter.
Oh, that's me. I'm a friend of Peter's. Hello. Yeah. Sorry. Yeah, Peter's got a funny voice. Yeah.
I recognise your voice from your emails.
Oh, Magda. Yeah. Hello.
So, Peter, an historian of chemistry and an amateur astronomer. He was in charge of the chemistry collections at the Science Museum in South Kensington for 24 years, after taking degrees in chemistry and history at Oxford University. In recent years, he's taken up the observation of double stars, and it is not badly affected by light pollution, which I think we can agree with, and have observed around 1,200 double and multiple stars. So can the Mexborough-Swinton Astronomical Society please welcome Dr. Peter J.T. Morris. Thank you.
Thank you.
Thank you.
Thank you. Thank you very much, everybody, for inviting me to give this talk. It's based on a paper I wrote in the Amateur Antiquarian Astronomer some time ago, of which I've now become assistant editor. Can I say before I start that you're all most welcome to join the talk by Emily Manda on the 7th of October at the Havering Astronomical Society, which is what I normally belong to, on the possibility of life in the clouds of Venus. She, in fact, is one of the people who wrote that very important paper about the detection of phosphine gas in the clouds of Venus. And you're very welcome to join us, and I've sent Roy and Steve the details of that. Okay, let's get going. Right, so my first slide then is, okay. Right. Using the astronomical list of 100 doubles, I chose 23 doubles which were bright, not to say both the primary and the secondary were fairly bright, but they were widely separated, so for the observer it did not become a test of skill in separating doubles, and they could be observed in small telescopes. But it also had to be high enough to be seen in the UK without being too close to the horizon, which would obviously affect the colours due to, of course, the diffraction of light. I might also say that the astronomical league is American, so some of the stars are quite very, very low for us. In fact, I think there's one that we can't see at all. Okay, now this is the list. I won't go into details of the list, but you can see that it has some fairly well-known double stars like Ashard, Almach, Mizar, and of course Alberio. So it's a fairly standard list of double stars. I tried to spread them out a bit, so 5 of them are circumpolar, 6 of them appear in the autumn, 4 during the winter, 4 during the spring, and 3 during the summer. Of course, if you're willing to stay up all night, there are certain times of the year when you could probably see nearly all of them. Now, some of these have multiple stars, some are binary, some are optical doubles, some are white, some are yellow and blue, and some are something else in between. Now, you might wonder, why do we choose white doubles when in fact we're looking at colour, but we'll come along to that in a moment. There are differences between all observers. You'll never get 2 sets of observers who will agree on the colours of double stars. We suspect that there are differences between older observers and modern ones. The only common ground on all of this, and the only sort of type of double that people agree about generally, are very obvious yellow and blue doubles. I mean, nobody, I think, doubts that Alberio is yellow and blue, although in fact that is an optical illusion, as we will see. Now, we therefore, when I say we, by the way, we, myself and my co-author, the American amateur astronomer and historian Bill Sheehan, we wanted to pair observers from the 19th century with an equal number of modern observers. The most famous of all double star observers, Wilhelm Struve, who works in what is now Estonia, was no good because he was obviously colourblind. So that really meant that the earliest collection of double stars we could use was William Smyth's famous Bedford catalogue, which is available in a reprint. Now, the other famous book of the 19th century was Thomas Webb's Celestial Objects for Common Telescope, which was being reprinted by Dover. So the 1917 edition, which in fact doesn't own that much for Webb himself, is still available in print. But the trouble is, which of those numerous observations were Webb's own observations? And in the end, by using some of the earlier editions from the 1917 one, I was able to ascertain that the ones I was using probably have been observed by Webb with those particular colours. But we were still lacking a third observer. And in the end, I decided to go for William Sadler Franks, who was later than the others. He published a series of papers in the monthly notices of the Royal Astronomical Society, basically during the First World War. And after an initial paper where he didn't list the colours at all, he listed the colours of many of the stars in the later papers, so that was extremely useful. Modern observers were hard to find. There is one observer called who also showed an observer called Bob Hogarth, who had published his list online. And as for the third modern observer, I decided to go for myself. I've just seen a link about the internet connection. I hope it's okay at your end. Right. So our next slide is a picture of William Henry Smyth using his 6-inch refractor at the Hartwell Observatory in Buckinghamshire, owned by his friend William John Lee, to whom he had sold his telescope in 1839. I might mention in passing that Smyth's grandson was William Baden-Powell, the founder of the Boy Scouts. So there's a connection between this and the Boy Scouts. Now, the next slide is of Thomas Webb and his wife Henrietta, probably in the 1870s. He was a clergyman. He ended up in Shropshire, if I remember correctly. He used a refractor and then he used a Calver reflector. But in choosing the stars that I recorded here, I tried to use one that he observed with his refractor rather than his reflector. And then finally, we have William Sadler Franks outside the Broxhurst Observatory at East Grinstead in 1913, where he ran it for Hanbury, of the pharmaceutical firm Anand and Hanbury. And of course, what he's most famous for these days is being the person who trained the young Patrick Moore as an astronomer, allowed Patrick Moore to help him in the observatory. And when a year later, in 1934, he was killed in a cycle accident, Patrick Moore, who was still a teenager at the time, but very tall, which I suspect may have had something to do with it, took over running the observatory. Now, this is Sissy Haas, and Sissy Haas picked up her telescope, which is only a 60mm telescope, quite old telescope, as you can see by the look of it, at a flea market, and that's how she got into double star observing. And she published a book, Double Stars for Small Telescope, which is now out of print and quite difficult to get hold of, but it's one of the few modern publications to deal with double stars in that way. And then in this picture, what I happened to find on the internet is a picture of the other modern observer I'm using, Bob Hogarth, who in fact is the man on the second left, with his hand in his pocket of the camera. So I'm very glad to say we have pictures of all the people included in the paper, except of course me. Now, so as an example of a white and white double, we have one of the brightest doubles in the sky, Zeta Ursae Majoris, known to one and all as MSAS, which of course is a very wide double with the star Alcor, which you can see in the picture here, and it's also a double in itself. And in fact, it's a very complex system altogether. There's about 10 stars, but we're not concerned with that here. And then Another example of a white and white double is not so well known, but in my opinion deserves to be known better, which is Theta Serpentis, which means, of course, it appears in the summer, or called Aya. And that's a very pretty double, and I do recommend it to you. Then the third example of a double appears in the autumn, but you can probably see it very well at the moment if it was clear, and that's Taiwan Piscium. Not quite as easy to see as the other we've seen so far, but nonetheless a quite easy double. And then we have what is known as 32 Comalapardatus. Now the trouble here is that the 32 is not actually a Flamsteed number. It was given it to the star by the Polish German astronomer Helibius. So it's known as 32 Comalapardatus, or more accurately Struve 1694. And then yellow and blue. Well, then we have Lambda Aeretus in the constellation of Aries. We have Iota Cancri. So they're nicely fun. The seasons there, one is in the autumn, the other is in the spring. We have Delta Sulphi, which of course is better known for being a variable star, but it's a double as well. Examples of other combinations, we have Eta Cassiopeiae, which is also known as the Easter egg double. We have 95 Hercules, and we have another double, summer double here, Gamma Phoenix. Now, what we then did was we made a table taking these 32 doubles and then briefly summarizing how each of those 6 observers, 3 of the 18th and early 20th century and 3 of the late 20th century, have seen these stars. Now, I'm not going to go into this in detail, just for the record. For example, Eta Cassiopeiae was seen by Smyth with pure pale white and purple, by Webb as yellow and pale garnet. I'll come back to that point in a moment. By Franks is pale yellow and ruddy purple. And then by Sissy Haas is yellow and almond brown. By Hoggebean, who doesn't go in for fancy colours, deep yellow and red, and by myself as yellow and purple. All of this in a way is quite significant, and I'll come back to that. Now, so I then did, well, but of course, because we can't sort of compare garnet with plum, for example, shall we say. I then sort of reduced them to their basic colours, white, yellow, purple, red, and so forth. Almond brown was a difficult one, so that gets counted off or other. And so I've summarised it in this way, just using the most basic colours, which makes it easier to compare and contrast the results of different observers. Again, I don't at this moment want to go into this in detail. Now, so for night vision. Okay, so we're looking at double stars. To the best of my knowledge, they're usually seen in the dark at night, and therefore we've got to consider night vision. Now, fundamentally, and forgive me if I'm telling you something you know already, but it's important for our topic. Our vision comes from rods and cones at the back of the retina. As you can see in this picture here, you've got the rod, which is rod-like, and you've got the cone, which looks like a cone with a sort of circular bit at the end of it. The cones are colour-specific, being red, blue and green, like the filters used in natural imaging. But night vision depends on the rods, which are not colour-specific. So we should not be able to tell colours in the dark. And indeed, if you think about it, we cannot detect the colours of earthbound objects in true darkness. The colour of your neighbour's door, for example, if it were completely dark. But planets reflect light and stars emit light. They are not dark, so we can see them. However, determining the colours of stars is a learned experience. At first blush, practically everybody sees all stars as white. This is partly because stars are surrounded by a black area. Colours of objects seen in isolation against a black surround are perceived in what physiologists call aperture or film mode. This is, of course, how we see stars and planets against the dark sky, and especially in a telescope eyepiece. Adapting to the dark surround drive the eyes towards right. Now, this effect of being driven towards right is remarkably demonstrated by the moon. The moon has an average albedo of 12%. That means if it were seen in daylight on Earth, it would look like weathered tarmac. But obviously, apart from the sea, we see it as white. This is a result of seeing a bright object against a dark background. By contrast, we may say so, by contrast, albedo is a good example of colour contrast. The main star in albedo is K2, and the B minus B, which is a measure of colour, is 1.13. This is clearly yellow, possibly even yellow-orange. The secondary is of stellar type B8, and the B minus B is minus 0.1. If we saw it on its own, which of course we don't, we will probably describe it as silvery white, or at the very, very most, silvery blue. It is in fact practically identical to Vigor, except in brightness, as Vigor is also B8 with a B minus B of 0.03. But when it's seen next to a very yellow star, we, and when I say we, virtually everybody, sees it as a deep cobalt blue. This is purely a matter of contrast. Now, to complicate masses even further, so we love to complicate masses, measurements see colour differently. Looking aside for the moment colour of green, red-green colour blindness, sorry, one could really say colour impairment these days, it has been shown that across most of the visible spectrum, males require a slightly longer wavelength than do females in order to experience the same hue. This is being tested in the laboratory. Annoying, like table connection here. Annoying may seem redder to a man than to a woman. Likewise, the green always appears greener to women than to men, to whom verdant objects appear a bit yellowy. But women have so far, sadly perhaps, made up only a small percentage of double star observers. Now, so does the telescope matter? I mean, typically, does the use of chromatic reflectors make a major difference between our older observers and our modern observers? But we still use chromatic reflectors. Look at the telescope that Sissy Hash was using in that picture. That is a node chromatic refractor. However, chromatic aberrations tend to only be important, at least in my own experience, with very bright objects such as Venus, the Moon, maybe the brighter planets like Jupiter. By contrast, most double stars, perhaps with the exception of MSAS, which I'll come back to, are relatively dim. However, this achromatic aberration may explain why some observers see tints in the colours of white pairs. The classic example is MSAS. I use a macroscope, so a macroscope can't suffer from chromatic aberration, and I recommend it, by the way, if you're interested in looking at double stars. And I see them as pure white. But I have been seeing as white and green, and even green and green. Could this be a result of achromatic aberration? I don't know. Aya as well, the summer double, which is white, can have yellow or other tints of colours, secondary colours. Even using a macroscope, I've seen pink and green and blue tints in Aya. Come to Gamma Arietis. The secondary of Gamma Arietis had tints for the observers, but there was no consensus about what these tints were. 32 Camelopardalis, which we saw. The secondary was seen as purple by the observers. I'll come back to that in a moment. And finally, Psi-1 Piscium is more likely to be seen as coloured by modern observers. So, if you're going to say chromatic aberration, we've still got to explain why that is the case. Now, that also raises the question, what colours are available to us? This may seem a silly question. For 19th century observers, the colours of stars were an open field. There could be any colour. Now we're aware that star colours are the result of the temperature of the stars. So therefore we're more limited in the star colours which we are permitted to see, if it were. Again, I will come back to all that. Now, if you look at the classic 19th century observer like Smyth, you get the most wonderful range of colour names. I mean, it's almost like the paint box of Farrow and Ball. I mean, you get apple green, and you get Damson and Garnet. Garnet was a favourite one of 19th century observers. Jason, lilac, melon, livid, radish, sardonyx, sea green. Wonderful. Let us turn from, before we go into the issue of colours in more detail, let us consider something that has nothing to do with the stars, namely the colours of the planet. The planets themselves only reflect the colour of the sun. Any colour they have is either because we're seeing near the horizon or because of some atmospheric or other effects on the planet. So it's fair to say that most people see Mercury as yellow or white. It's been argued that when you see it as yellow, that's because of the effect of diffraction near the horizon. Venus is invariably seen as white, or you might want to call it silver. Mars looks red, but in fact, particularly seen for a telescope, it becomes more orange. Jupiter is a difficult one in a way. They say it's yellow or tan, which I suppose is light brown, but to me it looks greenish. Saturn is yellow. Uranus is green or perhaps blue-green in the telescope. Neptune is definitely blue in the telescope because of its methane atmosphere. So this just shows us how we perceive colour in the sky quite apart from the double stars. And perhaps by comparing your own experience of looking at these planets, you can start to think, well, how do I see double stars? So, modern scientific colours. So, as I mentioned earlier, that we now feel ourselves to be more limited in the colours we can have. So what colours can we have? Blue, blue-white, white, yellow, orange, red. But this ignores personal perception, including colour blindness and the effect of contrast, which I've already mentioned. Now, if we look at the Planck curve or the black body curve for stars, by the way, I assume you all know what black bodies are. These are bodies which absorb and reflect, absorb and emit all the light that falls on them. In fact, I believe they're normally clay pots with an aperture on them, but no, there we go. If we consider stars to be black bodies, you get curves like this. So you've got a curve here for a red star, which is a cool red dwarf maybe, or a red giant. Then you've got a yellow star like the sun, and then you've got a blue star like Rigel, for example. All have their different colour maxima. Incidentally, we call a yellow star, which has a temperature very similar to that of the sun, yellow, but the actual colour of the sun is rather controversial. It's called yellow sometimes, and children invariably paint the sun as yellow. But it's been pointed out by the famous astronomer Alex Filippenko that snow is white. And if snow is a perfect reflector of the light of the sun, if the sun was yellow, snow should be yellow, and indeed Venus should be yellow. So the sun must be white, or is it? How would an observer on one of those planets would have been discovered orbiting Proxima Centauri see the sun? Would they see it as yellowish white, yellow, white? This is a topic for another time. So, and the other point I want to make is we can see all the stars. Now that might seem a bit of a funny thing to say, but it's very interesting in fact. But we can see most stars if we're close enough. We can either see them because the minimum temperature for nuclear fusion places stars at the red end of the visible region, and hence visible, and quantum theory, also known as the ultraviolet catastrophe, prevent the hottest star from only shining in the ultraviolet end of the spectrum, which we would do if it behaves as classical bodies and not quantum bodies. So That means we can see all the stars. But why so few colours? Given that violet and green exist in the solar spectrum, it might be wondered why there are no violet or green stars. That can be argued, but let's just take that as a fact for the moment. In short, it's because there's no black body which emits mainly green or violet radiation. This is a diagram of black body radiation showing the various colours and the line followed by black bodies of various temperatures. You will note that it starts just about in the red end, it goes through orange, it goes through yellow, but not for very long. Then it goes into a sort of rather muddy region, which is mainly white. Then it perhaps just passes what could be called turquoise or blue-green into just about ends up in blue. Note that green is far off and violet is nowhere near it either. So in theory, that's the reason why we have no green stars and no violet stars. It is not like a solar spectrum, it's a rather different kettle of fish, as you might say. So let's therefore move on. We cannot have blue stars and we can have purple stars or come with. Green stars, 95 Hercules, green and red for most of the Victorian observers. Modern observers tend to see it as yellow and yellow. MSAS, white and green for the 19th century observers. For most modern observers, white and white. That's probably an achromatic aberration effect. Gamma Andromedae, orange and green for most modern observers, yellow and blue. Gamma Delphini, yellow and green for the modern observers, yellow and yellow. So in the case of the 19th century observers, untrammeled by the knowledge they could not see ground stars, they saw green stars. Curious. Now, it has been argued that they saw green stars because green stars are formed by contrast, but a blue star placed next to a red star will look green in the same way that the secondary of Alberio looked blue placed next to a yellow star. Now that would work with 95 Hercules, which is red. It would just about work with Gamma Andromedae, which is orange being very close to red. Not quite just a convincing explanation for 32 Eridani, which is yellow, nor for Gamma Delphini, which is yellow, but MSAS is white. So the only feasible explanation, if we're going to exclude the possibility that green stars exist altogether, is that it must be some form of chromatic aberration. But blue-green stars, in some ways, are more interesting than stars. Because if we saw that diagram, it's just a hint of a possibility that we could see blue-green stars or turquoise stars and modern blue-green. Now, Alpha Hercules, seen by the 19th century observers, was orange and blue-green. Modern observers have no consensus on what the colours are. Planck tended to see blue-green, where his older predecessors, Smyth and Webb, saw green. So he saw Gamma Andromedae, 32 Eridani, and Gamma Delphini, a greenish blue rather than green. I wonder if that might have been because he had already picked up the idea that you can't see green. I have to confess, because I feel completely untrammeled by science, that I do see blue-green alone among modern observers. Now, purple. Why are there any purple stars? Epsilon Monocerotis was seen by the older observers as yellow and purple. Modern observers tend to see it as white and white, as I do. Alpha Canum Venaticorum, better known as Cor Carololi, they saw as white and purple. Modern observers have no consensus. I tend to see it as white and blue. Delta Uranus was seen by the 19th century trapeze as something in purple. Modern observers see it as yellow and something. So it's curious that the doubt has switched from the primary to the secondary. However, I have to confess, once again, untrammeled by the rules of science, I see purple, as in the case of Delta Uranus and see fluffy. This may be a result of using achromatic refractive, but purple fringes is one of the well-known effects of achromatism. We will return to this whole question of purple stars in the case of Eta Cassiopeiae later. Now, if we're trying to do this whole sort of thing scientifically, as you probably know, there are two sorts of things we have to take into account. Firstly, the spectral class of the star, whether it be O, B, A, F, G, K, or M, and I'm not going to use the sexist mnemonic here. Or you could look at it by pure observation, if you like, by taking the B minus B color index. So if you have a B minus B color index of about 0, you're basically looking at blue, white. Closer to 1, you get into white. Closer to 2, you're getting into yellow. Closer to 2, and then you're getting into sort of red, although even with the M stars, it says here that M stars only go up to 2. That's not true. There are some carbon stars which in fact they've got even higher B minus B values than that. But you get the general picture. But by using the B minus B color index, you should in theory be able to work out the color of the star. Now, so and we did that. Anyway, so I was saying that the first group of stars we had were B minus B were similar. And I want to emphasize, I don't mean they're similar across the whole of this group. I mean simply that they're only similar for the particular pair we're looking at. So it might be white and white, or it might be yellow and yellow, or it might be, say, yellow and blue, for example. The second group I had is where the primary has a higher B minus B value than the secondary. Now, in plain language, that means that the primary is yellower than the secondary. So you get something like Gamma Andromedae, which is orange and blue-white according to the scientific classification, or Beta Cygni, which is orange and blue-white as well. Whether you see it that way, of course, it doesn't matter. I'm just here using the scientific classification of the stars and BV values to work out what the color should be. Now, there's a third group which is incredibly more interesting, which is where the primary has a lower B minus B value than the secondary. Now, if you think about it, if the primary has a very low B minus B value, it's probably blue, and the secondary is probably yellow. And that, we're tending, if you look at the group here, we're tending to look at white and red or white and yellow. And we'll come back to that, because that's a very important group for our discussion. Now, when the doubles have similar B minus B values, modern observers tend to see them as being the same. There is this strange exception of key selfie, which makes me wonder if it's being properly catalogued, but we'll leave that aside. When the primary has a higher B minus B value than the secondary, all observers, 19th century modern observers, everybody sees them as yellow and blue, which is one reason why we see so many yellow and blue stars, because everybody agrees on them. When the primary has a lower B minus B value, and therefore we should see it as blue and yellow, that eye doesn't know what to do. Particularly with the early observers who didn't feel so troubled about what the colour should be, the eye gets completely confused, and we'll go into that in a little bit more detail. But I've now blown up that particular part of the table. And if we look at Eta Cassiopeiae, for example, Smyth storage is white and purple, Webb storage is yellow and reddish white, Planck storage is yellowish and purple. Sissy Haas, the modern observer, sees it as yellow and almond brown. Bob Hogerbean sees it as yellow and red, and I see it as yellow and purple. That's an classic example. If we take another example, for example, such as Lambda Aeretis, it should be white and maybe yellowish. But Smyth storage is yellowish and blue, almost the wrong way round. Webb storage is yellowish and greenish. Planck, unfortunately, I don't have a record for. Sissy Haas saw it as white and white, which is not too far off what it should be. Bob Hogerine sees it as yellow and bluish white, which is not right. And I managed to see it completely the wrong way round, because I see it as yellow and blue, when in fact, if anything, it should be blue and yellow. Then it's a complete reversal. And I could go through the others as well. I mean, for example, you've got Kappa Hercules, which should be yellow and orange, but my story is yellowish and reddish. Webb, probably influenced by my story, is yellowish and reddish. Planck's story is yellowish and orange, which is not too bad. Sissy Haas sees it as orange and reddish. Bob Hogerine sees them both as yellow, which is again coming fairly close to the scientific colours, and I see it once again as yellow and blue. So when we get a primary that has a lower B minus B value, it's bluer, in other words, than the secondary, the eye gets completely confused. I don't know why this is the case, but it undoubtedly is the case. So, conclusions to be gathered here. Most observers agree that, most observers agree that yellow and blue stars. If you've got yellow and blue stars, most observers see a yellow and blue star. Pre-modern observers saw green and purple much more than modern observers. Whether that was because they were untrammeled by expectations or whether they were using achromatic refractors, don't ask me, it's the case. Modern observers are more likely to see the scientific colours, in inverted commas, would mean that they're more likely to see yellow and blue. Pre-modern observers were more likely to see tints in white pairs, and that might be a result of chromatic aberration or poetic imagination. What are our next steps in this project? Bill Sheehan and I plan to recruit about 30 to 40 observers for the next stage. We need a good range of observers. We want to have young observers and old observers. We want to have a lot more women as well as the men. And we would like to get at least a few people from the BA-ME community, because they've hardly been represented in double star observing at all. And we want to ask them to record the colour of these doubles using a fairly small telescope of about 3 to 5 inches, probably a refractor, but a muscle off, or even a reflector would be fine. And we will give them a list of permitted colours, so they don't go off and start calling them apple green or plum or claret or garnet or whatever. We just want to know what is the basic colour that they see. And if one of your members will be interested in taking that project, I'm not quite sure how far along, how much longer, it will probably be a while, particularly with this COVID stuff going on, before we do that. But if anybody's interested, do drop me a line. So the other thing I would say is that if any of you, and it will be very grateful actually, if any of you were interested, will be interested in taking photographs of these stars, because I must admit that I'm not myself a photographer. Most images tell me that in fact it's quite difficult to take photographs of double stars. Apparently you need quite a large aperture, and then you need quite a large focal length. I'm told my internet connection.
Do you think it would help if some people turned off the videos?
Well, we're nearly finished.
Yeah, okay.
I hope we're okay there, by the way. I had another warning there. But as I say, if anybody would be interested in potentially taking images of some of these double stars, I would be very interested to get them, and we could possibly use them in a future article. I must ask though, if you were to take any images of these stars, that you do it pure and simple. I mean, use blue, green, and red, green, and blue set of reflectors. Don't try and make the stars look the colours they should be. That's exactly what we're not wanting. What we want is to see them as we should see them. And that in the case of one of the last group I was talking about, namely the primaries with a low B minus B, will be a very interesting thing to do. And in fact, one of the things that has been done in the past is that they've taken stars like that they've asked people what the colours they see, and then they show them a photograph of it. And interestingly, even when they see a photograph, they don't see the right colours. So it's a very, very interesting optical effect. Well, you'll be probably very happy to know that I'm now finished, and I'll be happy to take any questions. Thank you very much. So let me just put the gallery on so I can see everybody.
Okay, thank you, Peter. That was a really interesting talk. Just thinking back on some early photography work I did, and I tried to take pictures of constellations, especially when I was on holiday and couldn't take very much equipment. And I always found that I could get the color of the star to show a lot better if I had my camera slightly unfocused. Just, I didn't have a nice pinpoint star, and it really does bring out that bring out the different colors. Do you use a similar? Do you use a similar technique when you're observing?
Good question. I've not tried it because generally speaking, what you're trying to do is get a good separation.
Okay.
And to get a good separation, you want it to be well focused. But you raised a very interesting point. I have no doubt the reason why you were seeing the colours better in the photograph is because you were getting a bigger area.
Yeah.
And therefore there was a bigger area for the colour to show. That's interesting. That's an interesting point. I'm afraid there's so many security lights outside where I live at the moment. I've rather given up on observing right now, but maybe I'll try that sometime and see if that's an interesting point. It might be worth trying.
Okay.
It'll be interesting to see how the colour compared in unfocused rather than focused. I would imagine it would remain the same.
Right. Okay, ladies and gentlemen. As usual, we come to the part of the evening where we field any questions. Once again, I prefer you to put a digital hand up because that's easier than me having to go back and forward looking for people waving at me. So if you'd like to ask a question, put your hand up. Okay, Peter Lloyd, can you unmute your microphone, please?
Mm-hmm.
Yes, thank you, Peter. I just wanted to make a comment on the idea of getting these colours by photography. I've taken pictures of quite a few different double stars. They're all up on my website if anyone wants to see them. But usually I can see no colours in them at all. And even with Alvario, I had to really fiddle the thing, rack up the saturation so in order to get any colour to come out at all. And I think this may be partly what Paul was just saying, that if you're exactly in focus, then the image of the star doesn't cover enough pixels for the color rendering to come out. And so it may well be quite important to defocus your telescope slightly. I haven't tried it.
Okay, that's a good interesting point. I don't do imaging. That would make perfect sense to me, actually.
Can I just ask one other thing? When you're observing like this, are you careful to do it in total darkness?
Okay.
Do you observe in total darkness?
I don't have that benefit, I'm afraid.
Just
I do have quite bad light pollution, and also, particularly more recently, I've got a lot of lights around me as well. I dare say, but carry on.
that's sort of the normal artificial light that is these days predominantly white. The only reason I ask it, I didn't know whether you might be using a red light torch at any time.
Yes, I do. Well, but it is that.
It depends how bright that is. I discovered this by experience. When I moved to my current house, there was enough money left over to get somebody to build my observatory for me. And when the electrician put the lighting in, I said, I need red lights. And he said, yeah, that was fine. And he put me in 4 60-watt red lights, which was blindingly bright, but I used them for a time. And I was looking at Saturn one evening, and it looked distinctly cyan. And I thought, why is Saturn looking blue? And I realized that these bright red lights had simply killed my red vision.
Well, in fact, you were getting in fact, you were getting a kind of contrasting effect there. So you had the sort of redness in your eye, and it was making Saturn look a different colour, just as you would by seeing two stars next to each other, I think.
Maybe it's something like that. Thank you.
But,
Peter,
I think it was a
just
good warning.
another question. Peter Morris, your two collaborators, your modern observers, have the three of you had a colour test, or do you have a colour test card that you compare and contrast each other's vision with?
No, it's a good question. No, it's a good question. I have to say, when I call them collaborators, I don't know them that well. Kitty Hattie's book is famous. I've worked with her on another project, although to be honest, I didn't contribute much to it, where they were trying to measure the effect of aperture of different telescopes by doing loads and loads and loads of observations of certain double stars to see how large an aperture you needed to separate a star. But I found I wasn't very good at it, and I didn't really take part in that in the end. So I do know her, but she is a very, very shy person. I had a great deal of difficulty even persuading her to agree to the whole thing. Bob Hogerbean, I only know through the web. I bet he will be more willing. I bet, speaking for myself, but I possibly have a very slight colour blindness, yes.
Okay.
Very, very
Have we got any more questions?
But if I may just say one thing.
Yes, certainly.
She's very, very bright yellow. I mean, stars that for most people are yellow, she calls orange.
Okay.
Now, the one effect I was going to mention, and in fact I forgot to mention, and that is with older observers will see stars in more yellow. Because basically, if you're anything like my age or older, you're carrying around a pair of yellow filters with you, called your cornea. And as the cornea gets more yellow, you will start seeing the stars. The older observers start to see stars as being more yellow than young people, which is one reason why I want to get a range of ages.
Okay. Are you going to give your 30 guinea pigs an eye test, a colour test?
I think we might. I think we probably will ask them to carry. You can get tests on the internet. You can do. So we'll probably ask them to do that. Yes, you've got a good point. You have a good point there.
Okay, I'm looking around for questions. Michael Poxon, can you unmute yourself, please?
Yes, I have unmuted myself. Can you hear me?
I can, and welcome to you and to Sean Reynolds, who I see lurking in the back.
Yeah, he's working very hard on his phone.
Okay, Michael, your question, please.
My question is really about colour terms, because a person A might call a certain colour yellow, whereas person B might call that same colour in terms of wavelengths. They might call it white, for instance. I'm just wondering if you've considered the possibility of using a different method, something like the Hagen scale of colours. You know, which is a little bit more sort of objective.
Yes, that's a good point. I mean, I have to say, part of what we're trying to do is to capture how people see stars. We're not trying to measure in any way scientifically what the colour of a star is. Our interest is in the perception of a star, and that perception of a star is obviously affected by what colour you see. It was suggested to me by a friend at the Royal Greenwich Observatory that I should maybe give people a colour chart like you get when you buy paint, and so you could all agree that a star looks sort of burgundy or whatever. But yes, so maybe we could give them the fire and ball colour chart. But yes, again, that's a possibility, and we would have to discuss exactly. But I have to say, my own preference would be just to give them basic colours: yellow, white, blue, and so on, and just hope that they see the the colours that way. It's a bit like Saussure, because the British Saussure came up with a colour meter, which was a number of rotating wheels that you could turn to measure the colour of the sky, which was something rather similar. But yeah, these are all things we'll have to think about.
Tell you something else. I did my degree in linguistics, and quite a lot of the research I did there was on the way that different languages compartmentalise colours. For instance, Welsh has 3 words which all mean green. So possibly along with your young and old, and different sort of races, you might look at different countries as well. If you're sort of covering more than one country, of course, different languages also see colours differently.
Yes, that's right. I mean, in fact, we did have a bit in the paper about how the classical languages don't really have a colour for blue. I mean, this is arguable, but some people have argued that the classics didn't have blue. Yes, I mean, the whole question of languages, I mean, French, for example, I mean, Madda bought some wallpaper that looks yellow to us, but because it was a French wallpaper, it was described as vert. So,
Yeah.
So, yes,
I think it's a really good project. It's a really good idea.
Language is a very big problem. I think most of our observers will be English speaking. I'm not saying English because quite a few of them will probably be American, but they'll probably be English speaking. But I completely take your point.
Yeah, it's a good project though, isn't it? It's a really good idea you're doing there. I think so.
Yeah. So I'm just hoping we can get it off the ground. That's the big thing, particularly with the stuff.
I think we've got school here.
Thank you, Michael. Is there anybody else with a question? I'm looking around for waving hands, and I don't see any waving hands. I don't see any blue hands. So, ladies and gentlemen, Peter, thank you very much for an excellent talk. If you send Stephen the list of objects that you want photographing, I'm sure that some of our members would be only too happy to help out and take some images.
But it's in the paper. It's in the paper. It's in the paper I sent you. But I will send you a sort of easier to use table that I've got. I'll send that to you.
Okay, and we might even be able to persuade our friends in Spain and things to have a go at some of them as well. Trevor Worrell,
Thank you very much.
I notice thumbs up from Trevor, so that's a yes. So, ladies and gentlemen, can we give Peter a Mexman Swinton Astronomical Society thank you for this wonderful talk.
Thank you.
Thank you.
Thank you very much.